Okay, here is quiz. Now work this just as if we're working it in class. We have a mass on a spring. It's an ideal spring, which means that its mass is negligible. Now, when this thing oscillates, spring mass is actually moving up and down, and that's kind of variable, how much mass is actually moving in the spring. But if the spring is very light compared to the weight, we can kind of ignore that. In a more advanced course, we might well write the differential equation that would result. In any case, ignore the mass of the spring and assume that your net force is simply proportional to the displacement from equilibrium. Let's assume that this thing is oscillating up and down with an amplitude of 20 centimeters. That's about like this. Okay. And the maximum net force occurs when you're as far from as possible from equilibrium. Maximum positive displacement, maximum negative displacement from equilibrium. Maximum net force is 10 newtons. Amplitude is 20 centimeters. Okay, what's the equation of motion? What's the total energy? What's the speed when it's at 15 centimeters from equilibrium? When it's halfway from equilibrium? And when it's speed when it's a quarter cycle. The equilibrium. And when it's an eighth of a cycle. It's hard to read that from equilibrium, though that's what it is. I recommend that before you try to do anything with this, write down some fundamental concepts. What are the fundamental concepts behind the motion of this object, and how do we move from the fundamental concepts to the answers to these questions without using a bunch of formulas we don't fully understand? Now, if you got to pull out a formula to do it, if you really can't make the connection, and most people probably can't at this point, then pull out a formula, whatever it takes. One thing I'll tell you in advance, please don't use the equations of uniformly accelerated motion, because motion is not uniformly accelerated because the force is not uniform. Well, the mass is. Okay, so see what we can do with this, and then we'll proceed to analyze a few things. Okay, hopefully you paused and processed as much of this as you can, worked as much as you possibly can. Fundamental concepts. First of all, for an ideal spring, net force equals negative kx. Also, F net equals mass times acceleration. Acceleration is just the second time derivative of position. So we can relate position somehow to, well, we'll see. Now we've derived everything. Those are fundamental concepts. Results. Potential energy is 1/2 kx squared. How do we get that? We integrate the net force, which is negative kx, from equilibrium, which is at 0 to x. And you get negative kx squared over 2. That's the work done by the conservative force. Spring force being regarded as conservative. In the ideal spring, this is an ideal spring, so that the force is conservative, unlike, say, with this chain of rubber bands. Potential energy is equal and opposite to the work done by the conservative force. The work done by the conservative force is negative kx squared. So the potential energy is 1/2 kx squared. That's a big deal. It'll be very helpful in answering some of these questions. Also, I didn't specify any initial condition on this. I didn't say where it should be at t equals 0. So we're going to let x just equal a times the cosine of omega t. Where a, of course, is going to be the greatest possible value of x. Note a is the amplitude. And of course, that was given. So now you know what a is. Now, how do we get this? Well, by solving this equation, by setting mx double prime equal to negative kx. So I'll just put a little note over here that mx double prime equals negative kx implies that x equals, we'll just that implication sign and point it at the equation. Okay. So x equals a cosine of omega t. Now x is a function of t. We understand that. Its position, x, is a function of t. Now, since it's gone up and down, you might want to call the position y. That would be okay. And you can put the x-axis straight up if you like. Yeah, I mean, you can tilt it for an incline. You put the x-axis in any direction you want, as long as the y-axis then is 90 degrees counterclockwise from the x-axis, you have a right-hand coordinate system. So I'm going to use x because we're more familiar with it. Okay, well, with that much, stop again and think. Okay, what in the world, how can you answer these questions given these tools, which are fairly easy to understand if you know what the fundamental concepts are, you know how they're derived. Okay, well, hopefully you're all giving this some thought. Amplitude is 20 centimeters. We want to know what the equation of motion is. Well, the other thing we get out of mx double prime equals negative kx is actually we get a cosine of square root of k over m times t. And we call that omega. Okay, so x is then a cosine of omega t. We know the mass. What's the spring constant? What's the force constant? Can you get the force constant and therefore omega? If so, you're going to get x equals amplitude, which is 20 centimeters, times the cosine of whatever omega is. How do you get omega? Okay, you should understand that to get omega, your key is to get k. I didn't tell you what k was, but I gave you plenty of information to get k. hopefully you've gotten K. If not, pause and see if you can get it. How do we get K? We know that the maximum net force is 10 newtons, and that's going to occur when you're at the 20 centimeter mark. Okay. Now you can write an equation, but intuitively that tells you you're getting half a newton per centimeter. Okay. You got twice as many centimeters as you got newtons. Okay. So you got half as many newtons as you got centimeters. You got half a newton per centimeter. You can write an equation and determine this. And I'm going to leave that to you. K equals I'm going to go ahead and put omega here. Omega is the square root of K over M. K equals 1/2 Newton per centimeter, which is 50 newtons per meter. If you get a newton for every centimeter, half a newton for every centimeter, then in 100 centimeters, you're going to get 50 newtons. And sorry, if you're getting half a newton for every centimeter, then in a meter, which is 100 centimeters, you're going to get 50 newtons. Now you could write that as a formula, F equals negative Kx, and F equals 10 newtons when X equals 20 centimeters, and you can solve that for K. And it doesn't hurt to write that out and solve it. But it's kind of an intuitive concept, so I'm not going to write that formula out. K equals this. Mass is 0.2 kilograms. So omega is the square root of K over M, which is the square root of 50 newtons per meter divided by 0.2 kilograms. Okay, well, you're going to get 250 there. Square root of 256 is 16. Square root of 225 is 15. So you're much closer to 16 than 15. So I'm going to say that this is approximately 15.7 some. And then what are the units? We're pretty careless with units. So work out the units that you would get here. I'm going to work them out in a minute, but pause video and work them out. Okay, the units are square root of Newton, which is kilogram meter per second squared. And then you divide that by a meter and by a kilogram. You're going to get second squared in the denominator. You're going to take the square roots. You're going to have a second in the denominator. In other words, a negative second power of the second, a negative first power when you take the square root. So it's 15 reciprocal seconds. I'll write that as second to the negative 1. Or 15 radians per second. So now we can write our equation of motion. Approximately 15.7 radians per second times 2. Now you can make this as precise as you like, as precise as you need to answer whatever questions you might have about the motion here. Okay, so 20 centimeters, 15.7 radians per second times t. There's your equation of motion. So you got the equation of motion. What's the total energy? Work out the total energy. Okay, total energy is potential energy plus kinetic energy. It X equals 20 centimeters. V equals 0. So K equals 0. And U equals 1/2 kx squared. Now this big K is kinetic energy. You can tell this context. You wouldn't say that the total energy is potential energy plus the force constant. But just to be clear, make this K bigger than this K. Okay. This kinetic energy is 0 and potential energy is 1/2 kx squared, which equals 1/2 Ka squared. At X equals 20 centimeters. Well, 20 centimeters is your amplitude. That's the maximum possible value of X. So this is 1/2 of 50 newtons per meter. And I'm going to need a little space here, so I'm going to have to erase this little side note I made. Make sure you understand where this comes from. Okay, so let's get that a little later. Okay. Well, half of 50 is 25. 20 squared is 400, but of course, we're not going to multiply centimeters squared by newtons per meter if we are thinking. We're going to write this is 0.2 meters, and the square of 0.2 meters would be 0.04 meters squared. Okay. We go half of 0.04 is 0.02. 0.02 times 50 turns out to be 1 joule. And let me write this as 1/2 Newton per meter, or 1 Newton per meter times a meter squared. This is 1 Newton meter or 1 joule. So this is a 1 joule oscillator. Now, using that much information, what additional quantities can you calculate? Okay, well, let's go this one. What's the speed when it's 15 centimeters from equilibrium? And that could be plus or minus 15 centimeters. I didn't say what the X position was. I just said how far you are from equilibrium. It doesn't matter. You know your potential energy at that point, which potential energy 1/2 kx squared. X is 15 centimeters, which is 0.15 meters. Squared is 0.0225. Half a K is 25. Point 0.0225 times 25 is about. No, I'm going to let you check my numbers. I did that in my head. I don't completely trust it, but it seems about right. I think it's 0.45 joules. So static energy is the total energy minus U, which is 1 joule minus 0.45 joules. Equals 0.55 joules. Set that equal to 1/2 mv squared, and you have your speed at 15 centimeters, and you can do something similar to find the speed at any position. Okay. Now, speed when you're a quarter cycle from equilibrium, speed when you're eighth of a cycle from equilibrium. What that means is it's not worded quite correctly, but at the time, the cycle is measured in time. So a quarter of a cycle would be a quarter of the period. Okay. And an eighth of a cycle would be an eighth of the period. Now, if you want to find out what a quarter of the period or an eighth of the period is, you can find the period from omega. And then you could substitute that in to an equation for the speed or the velocity. Well, let's see how that might be done. Okay. First of all, if you haven't already done it, why don't you stop and calculate the period of this thing? So you know how long it takes to get to a quarter cycle from equilibrium, how long it takes to get to an eighth of a cycle from equilibrium. So please calculate that. Okay, well, hopefully you've done so. Now I'm in a little bit of a workspace as usual. Can't complain about the design. I designed it, so okay. Yeah, that's not any great or profound design by any means. Okay, so what's the period? I've scribbled in simple harmonic motion. Time for one cycle. One cycle is 2 pi radians. Omega is approximately 15, excuse me, 0.7 radians per second. And well, 2 pi is a little bit over 12, 12.5 roughly. Well, let's just calculate. So big T is often used to stand for the period. The period is two pi radians, which is how far you go at the angular displacement, if you will, corresponding to a complete cycle, divided by 15.7 radians per second. Okay, well, that's approximately 6.3 radians divided by 15.7 radians per second. And I'm going to use an approximation. Use your calculator. You'll get something more accurate than 15.7 when you calculate this. And you could use that and divide it into this. You're going to get something close to what I'm about to estimate. 16 into 63 is 4. This is somewhat less than 16. And this is somewhat less than 64. So I'm going to just say T is approximately then 4.4 seconds. Yeah, that's fairly close. Okay. And that's a nice, easy number to calculate with. Now, quarter cycle. Equilibrium. T equals what? Well, quarter cycle is a tenth of a second, right? And quarter cycle lasts 4/10 of a second. Quarter cycle is approximately 0.1 second. An eighth of a cycle, T equals 0.05 second. We could plug those times into the formula for the velocity. So how's that going to work out? Think that one through. Obviously, what we need is the formula for the velocity. Okay. Well, we need a formula for V of T. Well, we know X equals 20 centimeters times a cosine of 15.7 radians per second times T. So V equals X prime equals 20 centimeters times 15.7 radians per second times the cosine. And I'm going to have to get rid of this board. Okay, that would be times the cosine of 15 radians per second. You can't read that. The chalk just isn't working there. Or my hand isn't working well with the chalk. Okay, there's your velocity. Okay, so we can say that V of T is approximately equal to, because this 15.7 is approximate, we'll multiply the 15.7 by 20, and we get 314, sorry. It's not 314. Yeah, it is 314 centimeters per second. There's the cosine, 15.7 radians per second times T. Now that's kind of sloppy. I didn't leave myself enough room there. Should have worked over that way, but I don't want to stand and block the board, so here I am. Or, if we wish, 3.14 meters per second times the cosine of 15.7 radians per second times 10. All right, well now, I gotta do is plug in T equals 0.1 second, T equals 0.05 second, and you get a result. Turns out that 0.1 second gives you 1.57 radians. Cosine of 1.57 radians is cosine of 90 degrees, apparently, approximately. Okay, now my estimate 15.7 was fortunate, fortuitous, whatever. You can verify by doing the calculation that V of 1 second equals 0, because you got the cosine of basically 90 degrees. By 1.5 second radian per second by t, you get 1.1 second. You get 1.57 radians. Cosine of 1.57 radians is 0. Now, it's not going to come out exactly 0. So we'll say it's approximately 0. And V of 0.5 seconds is approximately equal to what? It's approximately equal to, well, you multiply. I'm tempted to call this pi over 4, but I'm not going to. You do the cosine of this thing, and you're going to get the square root of 2 over 2, which is like 0.707. And you multiply 0.7 times 3, you're going to get 2.1. And the 07 is going to give you 2.1. Getting my decimals messed up. It's late at night. Okay. 0.7 times 3 is 2.1, and you add 0.021, and then you got the 0.14. I'm thinking you get about 2.2 meters per second. All right, we'll take that. Might not be totally accurate, but you can get it very accurately. Okay, so that's just an answer to the question. Again, of what's the speed when you're a quarter cycle or an eighth of a cycle from equilibrium? We find the time for a cycle. We find the time for a quarter of a cycle or an eighth of a cycle. Cycle was 0.4 seconds, quarter of a cycle, eighth of a cycle, 1 second, 0.5 seconds. We used our equation of motion for x, took its derivative, got the equation of motion for, well, the equation for velocity is a function of time, and plug those numbers in, and that's what we got. Now, here's an easier way to get those results. I move over onto the other side of the board. No, I have nothing. No, I don't. Move this over just a little more. Yourself a little bit of room. There's not going to be much, but I can do it here. Okay. At a quarter cycle from equilibrium, we're at the maximum distance from equilibrium. So we're at 20 centimeters. So we know that the speed is going to be 0. So let's forget about that. That just confirms what we got here. And that confirms it in very simple terms. You know, you cycle, if you start from equilibrium, you go out to your maximum distance, which is 20 centimeters, back to equilibrium, 20 centimeters below equilibrium, back to equilibrium, quarter cycles up here. Eighth of cycles halfway between here and here. So an eighth of a cycle is, yep. I'm not going to say what I was just going to say because it would be wrong. Okay. Um, I was going to make a full circle with energy there, and I just realized that what I was about to do was incorrect. Okay, so I'm over that now. Okay. Uh, well, that answers all the questions. Um, I was going to ask another question about speed. Oh, I did ask a question about speed given x. Okay, so given your position x, you can figure out your speed from your total energy and your potential energy. There's even a formula that you could write. This formula here could be written as one half Ka squared equals one half Kx squared plus I'll just say plus K. We know K is one half mg squared. And we're going to get those symbols mixed in here. So we can always find K. Um, one half Ka squared minus one half Kx squared. And we did that in class, in our last class. Okay. Now I want to give you the unit circle picture of simple harmonic motion, which kind of summarizes a whole lot of stuff. Okay. Okay, I wasn't trying to draw a good circle. I just let my arm do it, and I actually came up with a fairly good one. Okay. Here's the x-axis. Here's the y-axis. Let's for the moment call this a unit circle. Then the radius is 1. Then if we have a point moving around this circle, okay, the point's going to be here. It's going to be here, 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 here. So let's say this is a typical point. Sometime we're here. And let's say that this circle represents motion with a period of 4/10 of a second. It's about like this. Okay, something like that. It's moving, you can see it moving. It's not faster than the eye can see, but it's moving kind of fast around this circle. So when are we at this point? Well, at some time we're at this point. If we're moving around here at hesitating. To relate to our example here where omega was about pi over 2 radians per second. Did I say that right? It is, and it's like 10 pi over 2 or 5 pi. You know where I got that pi over 2, that was It's in at 1.57 there. 5 pi radians per second. That will give us a period of 0.4 seconds, and that coincides with this mass of the spring. So that at time t, the angle that we've gone through is omega t. In this case, it's 5 pi radians per second times t. So if this is where we are at time t, then that's where we are in the circle at time t. What's our position on the x-axis at that time? Well, position on the x-axis corresponds to this point of the circle is going to be here. Well, x equals then cosine of omega t, because we know the circular definition of the trig functions. X would be cosine of omega t. Y would be sine of omega t. So as we move around the circle, the x coordinate starts here. We start at t equals 0, angle 0. And as we move around here, the x coordinate is going to move from here over to here and then back to here. If we keep moving around, then it's eventually we're going to get to the full cycle. It's going to come back here. So this x coordinate is moving back and forth. X equals cosine of omega t. Well, that's simple harmonic motion. It's simple harmonic motion with an amplitude of 1 unit, whatever the unit is for your unit circle. Now let's change that from unit circle to circle of radius 20 centimeters. What does that change? Well, that makes the circle 20 times as big and puts a unit centimeter on it. I don't have to draw a bigger circle. I can just declare that the radius is now, that the circle represents a radius of 20. We're representing a circle of radius 20 centimeters with this picture. And then now what's the x coordinate? Which is x equals the radius. Give me something up here. X equals 20 centimeters times the cosine of omega t. Or if you prefer, y equals 20 centimeters. It's hard to read that centimeter. It's not an exponent, it's a very tiny centimeter. Y equals 20 centimeters times the sine of omega t. What's the speed of this point on the circle? Well, the speed is going to be omega times the radius of the circle. Okay, does that make sense? Should. What's the direction? Well, here's the direction of your R vector. We're used to R vectors, so I'm going to call this vector from this point to this point the R vector. The R vector has direction 5 pi radians per second times t, or I don't have room to label it here. I'll have to write it over here. R equals 20 centimeters times the cosine of omega t times I plus the sine of omega t times j vector. And I think, no, I'm still on the screen. Okay. So V, magnitude of V is 5 radians per second times 20 centimeters. The V vector is 5 radians per second times a unit vector in this direction. This unit vector is perpendicular to the R vector. And you can work it out. You can see that this unit vector is going to be sine of omega t times I minus cosine of omega t times j. The position of the point on the x-axis is just the projection of this vector on the x-axis. We could call this vector R sub x, the x-coordinate of the R vector, which of course is 20 centimeters times the cosine of omega t. We can project this vector onto the x-axis, and it's going to interfere with my labeling of the R vector here. We'll stop things up just a little bit, fix that. So I'll label the R vector down here. Now, this projection is going to be a vector here. And that's going to be the x component of your velocity vector. Now, this relates to what we know about angular motion, right? It's just angular motion around a circle of radius r. How did I get the velocity? I multiplied the angular velocity by the radius. That's something hopefully we're very familiar with. And it gets even better than this. It clutters the picture up a little bit, but I think I'm going to go ahead and draw it. The acceleration vector is, well, it's the derivative of the velocity. But let's back up a second. The velocity vector is this, just from what we know about the geometry of this thing and angular motion. It's also the derivative of this. Now I'm mixing up my omegas and my 5 pi radians per second. So it might not be as clear as it would be. I used omega consistently. And amplitude, and I don't like the way that came out. Because here I've got 20 centimeters instead of amplitude. Well, I'm going to move away from our specific example. Instead of 20 centimeters, I'm just going to call that A. And then I'm going to clean the picture up a little more. I'm going to pause for a second. But what I'm going to do is simply replace 20 centimeters everywhere by A and let omega be unspecific. Okay, now I'm letting omega just be symbolic. Before I said, okay, related to this picture, it was 5 pi radians per second. Now I'm going to just label this circle. The angle here is now omega t, and I could call that angle theta, theta being a function of t. Circle has radius a, then x is a cosine omega t, y is a sine omega t. That's not part of our model, but it could be. We couldn't model in terms of that function. Okay, so your R is a cosine omega t I plus sine omega t j, etc. Velocity is omega a. The vector velocity is omega a times the sine of omega t I minus cosine omega t j. And now I can say what I started to say when I had things jumbled up a little bit. If I take the derivative of the R vector, I get the V vector. Now remember, when I built this V vector up, I simply took the components of the R vector and switched them around. I basically rotated the R vector 90 degrees this way to get the V vector. To get the direction of the V vector kit, the unit vector goes from this to this. Derivative does the same thing, and it's worth understanding that connection. If I want the acceleration vector, well, acceleration just v squared over r, right? And what's the direction of the acceleration? Back toward the center of the circle, because we're moving along a circle in a constant velocity. So I can say, acceleration equals v squared over r. Where v is just omega a. Where by v, I mean the speed of the particle going around the circle. And like this in this order better. Okay, so the speed of the particle in the circle is omega A. The vector velocity is what we have here, but we don't use that. We get the magnitude of the acceleration. The vector acceleration is back toward the center. The magnitude of the vector acceleration is omega squared A. And the direction back toward the center is just the opposite of the direction of the R vector, because the R vector is radial. Acceleration vector will be back toward the center or centripetal. And it's just going to be the negative of the unit vector. The unit vector for the acceleration vector is going to be the negative of the unit vector for the R vector. So we can have our acceleration vector here. In vector form, it's going to be negative cosine omega t I minus sine omega t times j. Of course, this is the derivative of this, and this is the derivative of this. We didn't use derivatives. We reasoned this out from other principles, from what we know about angular motion and so forth. The projection of this acceleration vector up here, well, it's getting a little messy, but it's going to be this vector, which we'll call A sub x. The x component of A is just omega squared A times the negative cosine of omega t. What we see then is that simple harmonic motion along the x-axis is easily modeled by considering a particle moving around a circle, radius equal to the amplitude of motion, angular velocity equal to the angular frequency. For a model here, we would let omega be 5 pi radians per second. The only place we got that is there, but I've replaced that by omega A. If we have another angular velocity, if we do the square root of k over m for another system, we're going to get some other angular velocity. That'll be our omega. That tells us how fast we're going around the unit circle. And then we imagine the projection on the x-axis of that point going around the unit circle. Now, not going to go. I'm going to relate this to simple harmonic angular motion, but we'll talk about that later. Okay. This is a powerful model. It's a powerful picture. Try to understand it. Basically, you're moving around this circle with some velocity. You have a centripetal acceleration, v squared over r. You just put directions on these vectors by pasting on the unit vectors and take the projection onto the x-axis or onto the y-axis if you want to use the sine. If you want to use some other angle, well, you can add a phase angle in here, but I'm not going to go there just yet. Okay. This is an important picture.